You guys remember we're doing an ANSYS activity today, so if you want to launch Workbench, when we can hit the ground running once the lecture starts. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Good, hanging in there. It's busy times, I know. Probably you guys have a lot of midterms and other classes, so always during this time, I know that just naturally and with the recorded lectures, I know not everyone's going to come to every lecture, and so for those of you that do come, I just want to say I appreciate it. I'm paid to be here, so I have to be here, but when you guys kind of come to class, it's always nicer than when less people come. So thank you guys for for choosing to spend your time here today. Okay, but today we have an exciting day, and so today is our next ANSYS activity. Okay, and this time we're going to be doing a finite element analysis on a signpost. Okay, and so the signpost looks like this, and so basically the dimensions of the signpost are basically what you would expect on like a freeway, right? And so if you look at the height right here, H1, this H1 here is 28 feet. And so this is not something that you're going to put outside your house unless you're a maniac. But this is something that basically tells you, where your exit's going to be. Okay. All right. And so this signpost here is going to be subjected to quite a few forces, right? And so first of all, because we have such a massive structure, or at least relative to the parts that we have been doing, we're going to consider the weight of all the different parts, and so that's going to be an important factor. Okay, and we also have forcing from the wind as well, right? And so we have a wind force that comes on the left side of the post here, and we have another wind force that kind of strikes the middle of the sign, just like that. Okay. All right, and so today we're going to be learning about quite a few new features in ANSYS that we haven't seen before, right? And so for the first time, we're going to be working with an assembly of parts, right? I know our bike crank was an assembly, but we just suppressed everything until it was just a single part. But this time we're not going to suppress anything. We're going to work with the whole thing. Okay. And then we're also going to learn how to apply weight. Okay. Because there's kind of a special convenient way to do that in ANSYS. Okay. And also we'll learn how to do a spatially varying load as well, right? And so if you look at this wind force here, this WX2, it's not a constant pressure, right? And so it's a pressure that increases, as you go up the post. Okay, and so we'll learn how to do that within ANSYS as well. Okay? All right, and so before we start, you can log on to Canvas, and if you go to the assignments page, and then you click on activity 3 for signpost, you can download the instructions, which you're going to need today. And you can also download the solid signpost geometry base, which is a design modeler part. Okay, and so go ahead and download those, and open up Workbench if you haven't already. Okay. And before we start, I do have one quick announcement. And so you might have gotten an email about this today, but I did post the midterm project. Okay, and so that's available for you on Canvas right now. And so if you go to the project page, you'll see that I've included the instructions. I've included the template for the report, and I've also included the rubric, which I'm going to use to grade the midterm project as well. Okay, as well as the 2 CAD files that you would need. Okay, and so I'm going to save. I do want to talk about the project, but I'm going to save it until Monday, just because today I want to make sure that we have enough time to get through the activity. Okay. But first thing on Monday, we're going to talk about the project and just kind of what I expect from it, and what you can look out for. But if you want to take an early look, then it's available for you. But just know that we're going to talk about it on Monday. Okay. And the due date for this project is October 29th, and so you guys have a little bit over a month to do it. Okay. All right. Any questions that I can answer before we get started with the activity? Okay, all right, so let's go ahead and get started. And so if you have Workbench open, let's go ahead and go with that, okay? And then just like before, we're going to do a static structural simulation. And so let's go ahead and click and drag static structural, just like we always do. Okay? And then let's go ahead and import the geometry, okay? And so let's go right click on geometry, go ahead and import, okay? And let's go ahead and browse for the file, okay? And it should load without any issues, because this geometry was created actually within design model. And so it should fit very, very well with ANSYS. Okay. All right. And so before we start, before we launch mechanical, let's go ahead and add a custom material. Okay. And so one material that we're going to need for this analysis is our aluminum 6061, okay? Because we're going to build the sign out of that, okay? And so just like we did with activity 2, we're going to go ahead and double click on engineering data, right? We're going to bring up our material data sheet here, right? And so let's go ahead and make a new material, aluminum 6061, okay? And then just like last time, we're going to give it an isotropic elasticity property. Okay. Okay. And then if you remember from last time, aluminum 6061 has a Young's modulus of 1 E7 PSI. Right? And so make sure that the units for the Young's modulus here are given in PSI. And the Poisson's ratio for this is 0.33. Okay. Okay. But we need one more thing actually. A question. Our question: is there a way to save materials for future use? Yeah, that's a good question. I think if you, I haven't done it before, but I think if you maybe if you let me look into it first. I'm sure there's a way, just because it seems like a very obvious thing to do. Especially if you're working with a big database of materials, I would think that there's a way to do that. But yeah, let me look into it, and I'll have an answer for you by next week. Okay. And so last time for last activity, we stopped there at the Young's modulus and Poisson's ratio. But for this one, we actually need one more property. And the other property that we're going to need is the density. Okay. Because remember, remember what I mentioned before, that the weight of this sign is going to be significant, right? And so we need to we need to know what the density of our material is in order to properly compute its weight. Okay. And so you're going to go on the left side of the screen here, and you're going to go click on the plus arrow for physical properties. Okay. And then you're going to click on density right here. Okay. Right. And so with your aluminum 6061 highlighted, let's go ahead and double click on density. Okay. And that's going to add our density field here. Okay. And if you look into the project specs, I've given you the density in terms of pounds per inches cubed. Okay. And then aluminum 6061 has a density of 0.0975 pounds per inches cubed. And so if you haven't done so already, go ahead and add the Young's modulus and the Poisson's ratio and the density for our aluminum.
I'm sorry, Professor, can you explain again how to add a density?
Yes. And so when you click on aluminum 6061 right here, then on the left-hand side, you'll see a list of all the different properties you can add for the material. Okay. And then density is under this this setting right here called physical properties. Okay. And so you're going to click on the plus arrow next to physical properties, and then density is going to be the first one on the list. And so with aluminum 6061 highlighted here on the middle screen, you just have to double click density. Or another way you can do is you can click density and just drag it onto aluminum 6061. And that's another way that you can do it. Yeah. Mm-hmm.
Got it. Thank you.
Yep. All right. Is everyone good at this point? Everyone's able to add the density to the aluminum as well as the Young's modulus and Poisson's ratio. Make sure your units are right. And so a few people were getting some strange answers with their previous activities because their units weren't right. And so you always want to double and triple check your units here. Okay. And so now that we've added the material, let's go ahead and open up ANSYS Mechanical. And so let's go ahead and close our material data sheet, and let's go ahead and double click model. Okay. And this is going to bring up the ANSYS Mechanical, where we're going to perform most of our analysis. Right. And for those of you in the lab, if you get a permission thing popping up, just close it. It's okay. Yeah.
Poisson's ratio is 0.33, right?
Yeah, 0.33. Mm-hmm. Right, so we'll give it a minute or two for ANSYS Mechanical to load. right. Spam, let's go ahead and get rid of it. Okay. And so if you open up your geometry, then you know, you'll see that the signpost looks like this. Right. And so here we can see we have several different parts. And so it's going to look a little bit different than the screenshots in the instructions if you're following along. Because just this year I've added this little base right here. And there's a very good reason for that we'll talk about later. But this should help make it a little bit more stable than what it was before. Okay. All right. And so the first thing we're going to do is we're going to notice that, you know, we're working with an assembly of parts. And so if you go to the left-hand side of the screen and you open up the geometry tab, okay, or the geometry drop down, you'll see that we have three parts of our geometry, right? And so first of all, we have the sign, okay? And so if we left click on the sign _ solid body, you can see that we, you know, it's going to highlight this part right here, okay? And then if we left click on post solid body, you can see that it's going to highlight, you know, this part of the post right here, okay? And then the last body that we have here is this WX2 application surface, right? And so it might be kind of hard to see what this is, but if you click on this and you rotate the sign over to the so that you can kind of see the back side of the sign, you can see that we have this kind of like almost like a strip of tape that goes down the length of the post, right? And so what this is this is going to be you know, the way that we're going to apply one of our wind forces, right? Because if you go back to the figure in the document, right, you'll see here that we have this this force here called WX2, and that's being applied on the left side of the signpost, right? And so this surface here, this piece of tape, is going to allow us to apply a force right down the whole length of the signpost. Is there a question?
Yeah, how did you add that surface there?
It was I do have a tutorial on this, but basically you have to open up this this model in Design Modeler and then create a what I call like a phantom surface, and then you project that onto your geometry. And so it consists of drawing a sketch and then taking that sketch and then projecting that onto your geometry to create kind of an additional surface.
Okay, so that's not like a created plane that you have like tangent to the post.
It's a plane is part of that. And so, you know, for this one in particular, there was a plane that was kind of offset from one of the usual planes. And I drew a sketch in that plane and then I projected that onto the surface. I have a tutorial on that that I think I'll probably post as like an appendix for the class, because it is useful. Because, you know, what this allows us to do here is it allows us to apply a force that spans, you know, multiple parts of the assembly, right? Because normally, if we wanted to apply a force, we could only do it on, you know, maybe this surface of the post, okay. And then for the cylindrical, you know, post part, you know, it's hard to select just one part of that, right? And so if you try to select any part of the post, you're just going to select the entire exterior surface. And so if you wanted to select just this part right here, then, you know, you couldn't do that without this. Right, question. So to strip a planar or curved surface. So it's a planar sketch. It's just projected onto a curved surface. Mm-hmm. All right. Yeah, it's a useful technique, and it's I think one of the more advanced ones that's useful for things like this. Okay. But you know what you'll see here is that on the left side is that this application surface has a question mark next to it, right? And so whenever you see a question mark like this in ANSYS, it means that there's something, ANSYS wants some information from you, or it wants you to set something, you know, before you can proceed, right? Because right now it doesn't have all the information that it needs in order to, you know, properly apply this. Okay. All right. So let me go ahead and change the units to inches here. Okay. And so if you look down at the bottom left of the screen with WX application surface highlighted, you'll see that we have one entry here highlighted in yellow, which is the thickness of that surface, right? And so, you know, the reason we have to specify thickness here is that within ANSYS, you know, ANSYS views this as a very, very thin surface, like almost like paper thin, right? And so it doesn't actually have any depth. And so if you kind of zoom in on this on the surface right here, it's really just almost like a piece of tape that's been taped on the side of the mod, right? But because we're doing a 3D simulation, and ANSYS actually counts this as a separate body within the simulation, then you need to actually give it some physical thickness in order for ANSYS to register for it. Okay. And so this thickness here, it's mostly I call it like a dummy value. And so the actual value that you put there isn't that important, but you need to actually include something in order for ANSYS to properly register for this. Okay? And so the most important thing for the surface here is that we want it to be really, really thin. And so, you know, we're going to supply a very small thickness here. Right? And so I think in the instructions, what I say is that the thickness should be 0.001 inches. Okay, so 1e minus 3. Okay. All right, and so after we've set that thickness, then you can see that it no longer has a blue question mark here. Okay, and so we have a green check mark here, and so we should be good to go. All right, any questions on this so far? Okay. Oh yeah.
I can't find the thickness.
Yeah.
And,
So
all the geometries that the three of them are like all question mark.
oh, they're all question mark. Let me check real quick. Oh, that's because you need to assign the materials. Yeah. Actually, that's a good segue because you know, one other thing that we need to do is we need to assign you know, a material to each of the parts, right? And so one of the things with working with assemblies, and you know, one of the nice things about working with assemblies is that you can assign different materials or different material properties to different parts of your model. Okay, and in particular for this one, we're going to make the sign here out of aluminum. Okay. Right. And so by clicking on sign solid body right here, you're going to go down to the bottom left of the screen, and you're going to go to the material assignment. Okay. And from here, you're going to change this assignment from structural steel to aluminum. Okay. Yeah.
What's that check, that box you can check?
Which one?
The one right there.
Oh, this one right here.
Yeah.
Yeah, that's a good question. So that's that's how you can specify to ANSYS that this is a parameter that you want to optimize. And so later on in the semester, I think it's activity 6 or 7. We're going to learn how to do design optimization in ANSYS. And so when you do design optimization, what ANSYS can do is that it can whatever you specify as a P, as a parameter, then ANSYS is going to automatically iterate over different types of materials, or some cases different dimensions for your design, and then it's going to find the optimal one for that. And so that's basically how you indicate to ANSYS which ones are your design parameters. Yeah, but we're going to go over that later in the semester. Pretty late, unfortunately, but it is pretty cool. All right, and so we're going to make this sign itself out of aluminum, but the post, because in this case the post is going to be handling most of the weight, or it's going to be supporting most of the weight of this sign. We're going to keep it as structural steel, because steel is a much stronger material than aluminum. Okay. Right, and so this is one of the nice things of working with an assembly, because you know, you can assign different properties to the different parts of the model. Okay. All right. Any questions on this so far? Yeah.
What about the strip?
The strip, you know, the strip is we can just leave it as structural steel because the strip itself is not going to be supporting any. It's not going to have any weight or support any weight, and so it kind of doesn't really matter what we select for the material for that. It's so thin, it's basically not there, but it's really its only purpose is allowing us to supply a force on that part. Yeah. Mm-hmm. All right. And so that's one of the first benefits of working with an assembly in ANSYS, that you can assign different properties. Okay. But you know, when you are working with an assembly of parts, you have to define how those parts connect to each other, right? And so if you go to the left side of the of our project outline here, and you go to the section called connections, okay? Right? And so what the connections define here is those connections define how the different parts of your assembly, how they're going to interact with each other once the simulation begins, okay? Right, and so you can see here we have three contact regions that are supplied for us. And so you can actually check what parts that they govern by clicking on them, right? And so unfortunately they don't have the best names, and so they're just given the name contact region 1, 2, and 3. Okay, well, let's go ahead and left click one of them. Okay, and we can see what parts are being connected here. Okay, right. So your guys might be a little bit different, but because these are generated automatically by ANSYS, and so I think the order in which it does it might be random. But for me, when I click on this first contact region, and I see here that there are two surfaces that are highlighted here, right? And so in blue right here, this is the, that was the application surface that we were talking about before, okay? And so this is where we're going to apply our force. And then the other surface in red here is the left side of the sign, right? And so what this tells us is that this contact region is between the strip of tape and the sign right here, okay? Hear this, okay? All right. And so what you can do in ANSYS is that you can determine how these two objects are going to interact in your simulation, okay? And the way that you do that is you go to the bottom left of the screen, okay? And you define the type of connection that they have. Okay? And so right now you see that they're bonded, right? And so what bonded means is that those two parts are basically going to act as one, right? And so basically the two parts are welded together. And so everything that one part does, the other part's going to follow suit, okay? And so bonded is the default for anytime when you have a connection region. And so that's what's going to, that's what ANSYS is going to assume, okay? But some of the other options you have here are no separation, okay? And so that basically tells ANSYS that these two parts here are not to be separated once the simulation begins, okay? But otherwise, they're they don't apply that much contact to each other. Okay. You can also apply a frictionless contact, and so that basically tells you that the two parts can slide past each other without any friction. Okay. And so I would say that's more relevant for a for a dynamic simulation where there's actually going to be relative motion between objects, but it's also an option here for statics as well. Okay. And you can also do rough and frictional. And so these basically say that, these two objects, they can move past each other, but there's going to be some friction in between. Okay? And so there's going to be an additional friction force that hinders their motion. Yeah.
What's the difference between bonded and no separation?
Yeah. And so bonded basically means that it's going to treat the two objects as one, right? But no separation means that they can still slide past each other. They just can't physically separate from each other.
Okay,
yeah. Yeah, most of the time you're going to use bonded, but there are some cases where, if you have like a roller or something, then you would do no separation. Okay, good question. And as for the difference between rough and frictional, honestly, I haven't done enough testing to really know the difference between them. But those are both options for you if you want to do a dynamic simulation. Yeah. Okay. And so for this project, we're not really going to do, anything with this, because we're going to assume that this signpost is all one part. And so, we're going to make all of our connections here bonded. Okay. And so for this one, you can see that this is the connection between the post and the sign. Okay. And so you can see that from this image here on the right. Okay. And so you can see that the actual contact region is here, right here. And then the third contact region is the contact between the piece of tape and our post, okay? And again, we're going to assume that these are bonded. All right. And so before we move on, I'm just going to give you a tip that I usually like to do for large, assemblies. For this one, it's not as useful, but for cases where you have a lot of different parts and a lot of different connections, it can be really useful to rename your contacts, okay? And so you can see here that ANSYS actually renamed this one already for us. But it's useful to give these it's useful to kind of take the extra 5 minutes to actually give all your contact regions names so that you can know how to refer to them later, right? And so to rename something, you can just highlight it and you can either hit F2 on your keyboard. And so that's the shortcut for renaming, or you can just simply right click and hit rename, okay? And so since this is the contact region between the application surface and the sign, okay, I'm gonna go ahead and rename it like that. Okay. This one is the contact between the sign and the post. And this one is between the application surface and the post. Okay. Right, so you don't have to do this, and so this is not going to affect your simulation in any way. But I find that it's useful to do, and especially for your project. And so the I'll tell you right now that I because this is a graduate class, I gave you guys a little bit of a challenging geometries for your project. And so there's going to be a lot of parts in your project geometries. And so going in and seeing where all the connections are and renaming them to something useful is going to save you a lot of trouble in the long run, because you might have to mess with these a little bit. Okay. All right, any questions on this? Okay. All right, and so that's contacts. And so I know we didn't do anything for it this time, but those are something that's important stuff to know. Okay. And so, I'm not going to go over the meshing stuff just because, I think you guys have enough knowledge right now to mesh it on your own. But I will get you guys started. Okay. And so at the very least, I want to have 2 method objects and 2 sizing objects. Okay. Okay. Because I want you to apply different meshing settings to the sign and different meshing settings to the post. Okay. And so for both the sign and the post, I want you to select things like the element shape, the element order, and the element size. Okay. And so when choosing your element size, I want you guys to think a lot about, what you expect, or where do you expect most of the weight, or where most of the stresses are going to be, and then pack most of your elements in that area. Okay. And in the regions where you expect, maybe they're not going to be that much stresses, you can leave that one mostly alone. Okay. All right, so I'm going to skip over the meshing, and so I'm going to let you guys handle that. But I am going to walk you through some of the boundary conditions, just because there's a couple new things here that I want to make sure that you guys get. Okay. All right, and so the first boundary condition that we're going to add is we need to apply the weights for all of these surfaces. Okay? And so there's a special way to do this that's really convenient. And so if you right click on static structural A5, okay, we'll go to insert, and you'll see that there's a boundary condition here called standard earth gravity. Okay. And so if you read this, description here, where it says that it inserts a boundary condition that simulates the gravitational effects on the body in the form of an external force. Okay. And so basically what this is going to do is that for each of your objects, it's going to compute the volume of the object. And it's going to take the volume and multiply it by the density, and then it's going to compute a weight for each of the objects in your simulation. Okay, and then it's going to automatically apply a downward force on that, based on its weight. Okay, and so this is really convenient because that's not the one that I wanted. My hand slipped. Okay. Let's go ahead and add standard earth gravity. Okay. And so this is really convenient because this basically handles any weight effects, and so we don't have to do any more than this. Okay. Right, so this is really nice, and so this is something that I kind of just learned recently, and so in previous years when I've had this activity, I've kind of made the students. I have no idea. It's creepy. Anyway. Anyway, so yeah, so in previous years, what I've had students do is I've had them apply separate forces on the top of the sign and on the top of the post to simulate the weight. But this is just such a more elegant way to do this, because then this automatically computes the weight, and then it automatically applies it to the surface. Right? And so for any finite element simulation where weight is a concern, or you think weight is going to be a significant part of the loading, this is something very easy that you can do. Okay. The only thing here is that you have to make sure that the direction of the gravity is in the direction that you want. Yeah, question?
So we don't have to apply that force on top of the sun now?
No, you don't. Yeah. So the figure is a little bit out of date because it's that was from the old activity where I actually had them apply the force on top, and so I think that's WZ1 and FZ1, and so I'm not going to have you guys do that. And so the way that you can do that really simply is just to do a standard Earth gravity. Okay.
But does this give like a super accurate representation of what effect it would have on the sun?
Yeah, actually would. Actually, I would say this is more accurate than applying the force externally, because then this applies the force all throughout the body. Because normally a gravity force, it's the force. It's not a single force that's acting on your head. It's a force that's distributed through all parts of your body. And so the standard Earth gravity will do exactly that. Instead
Is
of
that why we put the density of the aluminum?
Exactly.
Like by how many feet, the density is what it weighs.
exactly. Yep. Yep. All right. So that's standard Earth gravity, and so that's super convenient. Okay. All right. And so another part of this project is that one of the wind forces that you're applying is going to be applied at a point on this surface. Okay. And so let's go ahead and apply a force. Okay. All right. And so this is going to be a point force. And so even though on Monday I told you not to do this too much, but I do want to show you how to do it in case you do want to apply a point force. Okay. All right. And so to apply a force at a point, what you're going to do is you're going to go to this section of the bar. Okay. And make sure you're on point selector. Okay. And then what you're going to do is you're going to move your mouse around kind of the middle of the post, of the middle of the sign. Okay. And then until you kind of see it highlight a little bit. So it's a little bit hard to see, but if I kind of zoom in a little bit, and you can see I bring my mouse to the middle, towards the middle of the sign, then you can see that little dot that's showing up as I move my mouse over there, right? And so it should be right in the geometric center of the sign. Okay. And so what you're going to do is you're going to select that point, and you're going to hit apply right here. Okay. And then now you can apply a force on that point. Okay. So again, usually you don't want to do this because especially in this case, because this is a wind force. And so normally the wind is a distributed force across the entire surface of the sign. But just for education's sake, I do want to show you guys how to apply a force at a point. Okay. And if you're wondering how this point got here, this point is not something that's in there by default. This is another thing that I went and I projected a point onto the surface. Yeah. And so very similar to this application surface, which we'll use in 5 minutes. I went and I took a point and I projected it onto the sign for that.
Within the sketch.
Yeah, within the sketch. Yeah. Yeah. So that's something that you can do if you want to apply a force or some kind of boundary condition at a specific point within your model. You can go into the sketching tool and project a point. A question?
No, sir.
Okay. All right. All right, question. So does ANSYS select geometrical center or center of mass due to uniform density? Yeah, so ANSYS does assume that the density is uniform all throughout. And so if you do want to localize that gravity force at a certain point, it's going to be at the center of mass. But the way that ANSYS actually implements it is that it kind of implements lots of tiny forces all throughout the entire model, for the weight, because the gravity force is actually something that's distributed all throughout the volume of the body. Yeah. Okay, and so you can go ahead and apply the force there. And so I believe it's a force in the y direction. And so the most convenient would be changing this to components and doing y. All right, so the other thing I want to walk you guys through before I let you guys work on the assignment is how to actually apply the spatially varying wind force here on the side. Okay. Okay. And so I believe this is implemented as a pressure.
How many pounds for the force?
For the wind force, I believe it was, I want to say, let me look at this, see. FY
8,000.
8,000 pounds. Yes. Mhm. All right. And so the last force, and so the last load here that we're going to apply is the spatially varying pressure on the strip. Okay. And so let's go ahead and right-click static structural A5 and then go to pressure. Okay. And then for the surface, you're going to select the little strip of tape here. Okay. And so make sure that you're only selecting just this surface. Okay. And so with the pressure, with that surface highlighted, we're going to go ahead and apply that to our pressure boundary condition. Okay. Yep. Right. And then for the magnitude, normally, for the magnitude of pressures like this, we normally supply just a single value. But for a case like this, where the force is changing with the, changing with space, right, or it's varying, then what we can do here is we can implement a function. Okay. And so we go down to the magnitude section down here. Okay. Right. Normally we would just enter a number. And so, normally we say like maybe 5,000 or something like that. Right. Okay. But instead of that, what we're going to do is we're going to input a function. And so to input a function, and so you're going to do this basically the same way you do in Excel. And so you're going to hit an equal sign. Okay. And so the equal sign basically denotes that your force or that your load is going to be a function. Okay. And the function that we're going to input in this one is just going to be a very simple one. And so we're going to do 0.1 times z. Okay. And so that basically says that the pressure that we're going to apply depends on the z coordinate, or depends on the height of where we are on the signpost. Okay. And our modifier there is going to be 0.1. Okay. And then you can go ahead and hit enter once you're done with that. Okay. Okay. All right. And so actually, let me go ahead and fill this in just so that we know. All right. Okay. And so, one thing you want to make sure is that you want to make sure that you're in the right units for this. Okay. And so, you want to make sure that you're in PSI right here. Okay. And so make sure that your units are in inches and pound force. And so the bottom one here when you're entering that function. I'm actually not sure why it's not showing up. Pressure. So let me do is equal to 1 times C. Normally it should show a what the magnitude of that pressure load is here. And so if you look at the figure in the activity, you should see that there's kind of a color bar here that shows you the magnitude of the force. For some reason, it's not showing up. It's not showing up here for some reason. But anyway, I'm hoping that it's fine. Is everyone else getting the same? Was anyone else able to see the magnitudes of their pressure force here on this region of the screen?
You have to run the simulation maybe first?
Yeah, maybe. Yeah, maybe you have to run the simulation in order to see. But
I think I see it.
oh, you see it on yours? Okay.
It's like something like this. It's a scale.
Yeah, yeah. It should be a color scale that shows that. Yeah. All right. So if you have it, that's great. But if you don't, I think it's okay for now. Okay, looks like some people at home have it. Maybe just the versions here in the lab, they phase that out of this version. But okay, and so that's all the new stuff in this activity. And so we have about 35 minutes left of the lecture. Okay? And so you guys can use this time to finish up the activity. Okay, so make sure you input the meshing settings. I think for the solution results, I think I gave you quite a few solution plots to do. Okay. And then from there, you can just go ahead and work on it. And so why don't you guys work on it for the next 20 minutes. And then I'll bring it back just to kind of explain just the last few problems of this homework. Okay. So go ahead and work on the meshing, try to see if you can get the simulation results. And then we'll bring it back here in 20 minutes. Okay.
So all we gotta do is mesh it now and then answer the question.
Yep.
Okay,
Yep.
cool.
Yep.
Thanks.
Yeah. So if you're having any trouble, just raise your hand. Or if you're on Zoom, just put something in the chat and I'll come around. Okay. Right. Can you try, go ahead and try and measure? It is check marked and the geometry is showing up. And so I'm hoping that it's, and you need to measure.
Fully correct, yeah.
So go ahead and apply measuring settings or fill those out and see if we can run this.
Just started to be.
Oh, yeah, maybe that's why you're saying wasn't assigned for anything. Yeah, it's usually structural steel. You can try starting a new project and see if it's there.
Oh, for T.
Yeah, well, if that doesn't show up, then, right? Yeah, I've never seen that before. Structural steel. But yeah, I actually, right when you have the.
Yeah, exactly. I mean, dude, at that point, it's all.
So these are, so this is the material way to.
Scroll down here, I put that shit.
Go to.
Yeah, I write that all the time. No, bro, if anything, I think you.
Would you like to?
do that? Practice
I
it.
think structural steel should. Yeah, so good
Yeah,
question.
that you should definitely.
Okay.
Like, I mean, I can do
How are you
like,
gonna price structural?
some calculating stuff, but like, you know what I mean? But like, making it super complicated. Been years. First time, 2 years since I've been, yeah, it's complicated. So I think you might have, since the last time for that. And for that, I'm kind of in like classes. So like, usually when I do the homework, I'll do it. When I have it, when I don't, I just do it like, like, in the first couple of weeks, I'll do it. Pretty soon I'm getting that.
Oh.
Yeah, that's what I'm gonna do. Doing English, I got 1+ grad 2. Bro, that's why I was like, it's not tough. It's not.
So you don't have to worry about
There's so much.
so there's always gonna be some, a little bit of measurement.
You can't do that on the thing.
Like it's.
Because we're not gonna have access to the computer, so we're not gonna give you.
Whenever you have a sensitive part, there's gonna be something that's not.
Like, those items are-
Same thing with the.
Just something, you know, this thing.
It's okay. That's okay. So basically, the ANSYS will treat them as if they're one.
Like the,
Yeah. Yep.
What's the difference between patch confirming and patch independent?
We'll go over that later on when we do kind of more advanced meshing techniques. It has to do with how ANSYS is trying to do the hexagonal mesh.
Okay.
Yeah, so they're basically different techniques for it. It's a little bit hard to get into right now without kind of diving too deep. But we will go over that.
It just gave me the option to change it, that's why I was.
Okay, yeah, just go with the default. That's good.
Okay.
Question. Oh, yes. Oh, fixed constraint. Yeah, don't forget your fixed constraint, everyone. So that it's your signpost is going to be fixed to the ground, and so it's going to be on the bottom surface. Yeah. I think I just mentioned it in a sentence, at the end. Yeah. Mhm. That would help.
Should we highlight just the bottom, or should we highlight like the whole The whole.
Just the bottom is fine. Yep. Sure.
You start to see the light kind of warping around like the structure. Is that-
It is, yes. And so what's happening there is that it's the elements are kind of trying to fit into that space, but because they're kind of too big, they're kind of stick out.
Got it.
So that is a good indication. Yeah.
It's like 20 feet. Like, point four. Why does it look so different? Look like a 0.4 element size with like extremely tiny.
You put 20.4 inches. Yeah.
You see, because like the total size of this is 20 feet.
Yeah.
Four.
Oh, so that's the flag. So this is the feature size. And so what that's another thing we'll go over in advanced session. So
It is there right here.
right. So this is looking for any features that are smaller than 0.4 inches and automatically hit it.
Wait, so with 0.4
It will be very fun. So try something north of. Try something like 3 or 4.
3 or 4 inches.
Usually I go show you the default is here, and I go a little bit flatter. That's usually the first step.
6 inches.
So
Mhm.
over about the mesh.
Yeah, so just choose between X dominant and X. We'll go over the other options once we get to more advanced meshing later on. But I just want you to make a choice between cats and X.
So I'm planning a refinement right there, where
Yep.
the connection assignment is supposed to, but
Mhm.
my refinement for this one is just faceless. But I want to include like this line to just issues and then this area.
Yeah, so you can do control clicking. So you can click on this face,
This is-
and then you can switch to this one right here. I think if you select that face, it should automatically do that edge too. That edge is connected to that.
Because this face is selected, these faces.
Yeah.
But it's not like defining this.
Oh, it's not refined. Try just choosing that edge or making another refinement just around.
So it's cool to make like more than one refinement.
Yeah.
at the same
Oh,
time.
yeah.
Okay. This is amazing, right?
Yep. I do see a question on Zoom, so let me come back for that. Is there a tool available for checking dimension of the geometry? Yes. And so one thing you can quickly do is if you look at the bottom of the screen here, you'll see that there's a ruler, right? And so this kind of gives you a rough idea for how big your geometry is. But if you want to look at, just the bounding box of the geometry, if you go click on geometry right here, let me go ahead and clear this. And then you go to bounding box. Right? And so if you go to bounding box under geometry, then this one right here will tell you approximately how big your geometry is in each direction. Yeah. And so the Z direction, you can see we have 438 inches. The X direction, we have a length of 167. And then Y is a thickness about 36 inches. Yeah. Mm-hmm.
Question.
Yep.
Sorry, I have questions.
Oh, no problem.
So I'm choosing the hex dominant.
Yep.
Elements size, but then I'm getting a lot of the texture features.
Whenever you add refinement to a part of an object, it's going to switch to texture. Because the refinement algorithm only works for tenths.
Yeah, okay. But this is acceptable, right?
Oh, yeah, yeah.
Even though it's a rectangle.
Yeah.
Okay, that's great.
As long as it runs, right? You get that.
All right.
Yep. Oh, it's on the strip. What's the thickness of your? Try changing it. Yeah. Try changing it to 0.0. Yeah, it's one of those sensitive things where normally something small like that, if it's not above a certain threshold, it becomes a certain. Yeah, these things are. Oh, I see. I give it a try now. Let me go help. So actually, the hexameters are going to be more. They're more balanced. And so they're going to be they're actually superior. So actually, something that's not so. You're trying to but generally, they're not superior. Just that they don't look good. If you can put hexameter, that's going to actually be and in fact, well, unfortunately, if you have a there.
I messed up the units of
Oh, I see. Oh, okay. If you just change the units here, go ahead and close the cancel and reload the cancel. It'll save all your data. It'll just update the material. Yeah. So you don't have to. Yeah. Oh. Oh, yeah, 2.5 and then pretty small. So they are. Yeah, so the I don't know, 10 should be okay. So for that one that I did up there. So yeah, anything in the layer, it'll finish eventually. So you can see that it's still going, it's still changing the colors. But yeah, try try to see, let's see how many elements come out. It's still going. So it's not, but generally, it's usually better to start with a course just to make sure that you get it. Yeah, so for those other activities, they were the objects themselves. So if you look at, this is the size of the groups. So for the other activities, the diagram itself, 2.5 mm on that one is not as significant. Yeah, it'll try its best, but it's yeah. So one actually someone on this that you can move. So this will kind of give you an approximate the next degree. This is right here. It's 910. So if you kind of use that as a reference.
About that application surface.
Yeah.
So we as point.
Yes.
Like what was the case? 0.000. So it starts to be
So it's going to have a little bit of difference because it's basically that. And so the thicker or thinner it is, you're applying the force. We're not. It's
just
interesting.
propagating the force.
Exactly.
Next surface.
Exactly.
Obviously what I understand that the surface more thicker surfaces right?
Yes. Yeah, technically, the thinner it is, but it's but sometimes you don't want it too thin. But it can happen sometimes if you have it too thin, then it's going to be hard for the computer. If you have it like say something extreme, 1 times 10 to the minus 16, and then you start to run up to numerical accuracy. So, but everything in the computer is done with floating point operations. So if you try to multiply by 1 times 10 to the minus 16, multiply by 10,000, that's going to be. So there's I think you make it 1 T minus 4, that's going to be a little more accurate. But yeah, there's only so far. So we perfect.
Yeah, so. Like all okay, yes, I'm in case. For standard Earth gravity, I think it does all bodies. I don't know if there's a way that you can select which ones. If you only want to do it for certain objects, you can just remove standard Earth gravity and apply just force manually for the weights. That's one way you can do it. But for certain cases where like you would probably want to do that for a case where you have one object that's really light. You don't want to apply too much to that. But if it's already really light, then it's already not. And so if you did want to do it, you have to kind of remove that and do the force individually. But for most cases, I think this is what. So,
Yeah. I thought that I really find this, like since it's a cylinder,
Yeah.
and that's where most of our elements are in the most sci-fi.
Yeah. Let's check this.
It's 84,000.
For these ones, actually try running it and see. It'll tell you right away. So it won't do it.
Anybody else on the bike crank, I had something like 200,000.
Okay. Well, this is
That's
less.
just my accent. I thought it was 23,000, but I've never seen it just like totally black. Like,
I mean, this is less than that, and so you might go with it. I mean, I would try it.
but I mean, this means it's really well modeled. Right?
Yeah.
It's like it's completely solid. The pictures are good.
Yeah.
Okay. So yeah, let's run that and see.
Yeah. If it works, it works. But if it doesn't, it'll tell you. Because these are not better than the solution. You can do that. If you yeah, we'll take it go.
Okay, just standard equipment. max deformation.
So this one I actually did quite a bit. Actually. So it's actually normal in each direction. But you can start with just deformation. And then up there, I have deformation and stress.
Okay,
So those are the first
the
two.
whole body.
Yeah, the whole one. Okay.
Deformation. Whole body, right?
So that basically is a number that multiplies the size of the element. So refinement of 1 basically means that it's like 1 plus the refinement. And so refinement of 1 means that the elements are going to be twice as small, and refinement of 2 is 3 times small. Refinement of 3 is 4 times small.
Okay, so would it be safe to say that?
It's just a way to apply. So generally, you want to apply the refinement where you think the stress is going to be. So wherever you think the stresses are going to be high, where do you think it's going to be?
Okay,
You can run it first. So like you don't have to apply a refinement right away. And so what I like to do sometimes is I like to just do the basic measurement settings first. I'll give it a run. And then if I see a place where I got some stress concentration, then I'll
find it. That's fine. Yeah. One more thing. Where can I check the schemes?
oh yes, oh that's true. We talked about that.
Right.
So if you click on mesh right there. Actually, so the under quality. And so if you yeah, so this right here. So if you look at mesh metrics, click on that. You can change that. So there's a lot of metrics for quality. And so let's change it to speed. Okay, so you can see here that yeah, typically you're going to get a max speedness of around 1. That's always just 1 random number.
The average is kind of which one is that?
Exactly. So your mesh is looking pretty good. Your average speedness is less than 0.2. You can look at the distribution. So most of your features is this one right here, which is good. So that's it. Okay, cool. All right, I'll go from the thing. Get results.
This is what it should say, right? All bodies.
Yeah.
Okay, I'm just certain ones.
Okay, let me go.
These are the results. In a second.
Usually it fails to make a hex dominant because the elements are actually too big. But if it's failing for a hex dominant, the hex dominant is weird sometimes. So like some computers just and some computers that just some days just refuse to do a hex mesh. And so for those, this, I mean, this looks really small to me already.
Yeah.
And so I don't think you would want to refine anymore. And so it could just be that your computer's just kind of not happy today. And so you can just switch it to tetrabeans and that's okay.
Okay.
And it's unfortunate. And I haven't really been able to pin it down, unfortunately. It's just kind of a really annoying thing, but yeah, sometimes it happens and sometimes it's
Well, I can use
you can do automatic. I think that's okay. But for automatic, I think most times we'll choose tetrabeans. So if you want to use hexes, then you have to come in. So. Yeah. So go back to that body size. And so you're selecting the D feature size. And so the size that you want is the L size, which is SL. Yeah, so the D feature is we're going to talk about it later in the semester, but one feature that ANSYS has is that if it finds a magical feature, like say you have like a weird nail that comes out like this, and it's smaller than 0.2 inches, then the mesh is just going to ignore it, which is really nice actually, because that, because if it was there, it would try to mesh around it, which is going to be but for the element size, you want to set the element size.
Yeah, so it's completely not. Look at this thing, it's like all one solid color, and you just have a huge stress concentration.
Okay. Let me look at your strip. Let me see your first. Yeah. Let me see your fourth choice. Can you try suppressing? Let's try suppressing the response. Oh, yeah. I think I have to take a closer look. Let me talk to the class. This person. All right, guys, let's bring it back for just for 10 more minutes. We have 10 more minutes left in the lecture, and so I do want to talk about the rest of the activity a little bit. All right, so everyone on Zoom, come back to. Okay, and so what you guys are working on right now is kind of like the first simulation for this, but there's a bit more that I want you guys to do afterwards. Okay. All right. And so if you're able to get simulation results, you'll basically have everything up to problem 4. Okay. Of course, you have to show the screenshots and the activity report just as normal. Okay. And I have some questions for you to answer here. Right. All right. And so problem 5, problem 5 is where we're going to start getting into design a little bit, right? And so remember, and this class is called Computer Applications and Engineering Design. And so we haven't done any design yet. And so, this is going to be our first taste of actually doing some design work in this class, right? And so, your results might vary, depending on your mesh density. But if you look at my results here, you can see that for the equivalent stress, I have a maximum equivalent stress of 28,623 PSI, okay? And that's occurring here at the bottom of the post. And so if we are, assuming, a certain failure criteria for this post, this is likely to fail. And so what I want you to do in problem 5 is I want you to basically redesign the post, okay? And so you can choose a lot of different ways to redesign it. Okay? You can do something as simple as changing the material, and so you can input a different material for this, and then that will lower the stresses, okay? Because it's going to have a different Young's modulus. Or you can actually modify the geometry of the post, which I think is the more interesting thing to do. And so let me show you just how to do that really quick, just because we haven't done too much of Design Modeler. Okay, and so I'm going to go ahead and exit ANSYS Mechanical here. Okay. And then what I'm going to do is I'm going to edit the geometry in Design Modeler. And so go back to Workbench here. Go ahead and right-click on Geometry, and then Edit Geometry in Design Modeler. Okay. And so this is going to open up ANSYS Design Modeler from the Workbench. And then from there, you'll be able to modify different aspects of the geometry. Okay.
Have that fillet within the ANSYS geometry?
I did, yes.
Okay.
Yeah, because that's not in the screenshots in the PDF, I know, but it's something that I added recently because.
Right, and you can have stress distribution there.
Right, yes, because what was happening before is that the bottom of this post used to be just flat, and then all the stress concentration was at this kind of edge right here, which we'll talk about later on in the class. But whenever you have like an edge, a sharp edge, then those are likely places for stress concentration, but those are not real stresses. And so what you'll see there is kind of artificially high stresses. And so I added this fillet here to kind of balance that out to make sure you don't get that. But anyway, and so what you can do here is that you can modify the geometry of this signpost to be whatever you want. Yes, it's a singularity basically. Mm-hmm. And so one popular way that people have designed the signpost in the past is they've just simply made it bigger, okay, or a bigger cross section, okay. And so it's unfortunately it's a little bit disorganized, but if you go to sketch 1 right here, and so you go to XY plane sketch 1, this is the circle that created the sketch for the post, okay. And you can see right here in the bottom left that the dimension for this circle, the diameter is 1.12 feet, okay. And so what we can do is we can increase this diameter. And so let me go ahead and increase this to, maybe just a modest increase of 1.25. Okay. All right, and so I've increased the diameter here. Whenever you change the geometry, you have to click on this lightning bolt icon here for generate. Okay. And then it was a little bit hard to see, but the post actually did get a little bit thicker. Okay. And so let's go ahead and close this. And let's go ahead and relaunch mechanical. Okay. You'll get a warning here that it says that upstream data needs to be reread. And so you can just click yes, because we changed the geometry. So we'll let that load. Okay, still loading. Come on. Okay. I think we're back. Okay. And so it's a little bit hard to tell, but the post actually is a little bit wider. So let me go ahead and run my simulation. Okay. The nice thing about that is that it's going to save all my settings. The only thing it updated was just the geometry. Okay. Okay. No access, that's fine. Okay. And if I look at the equivalent stress here, if you remember before, this used to be 28,000, but even just making a modest increase in the diameter, I've reduced the stress down to about 21,000. Okay. Right. And so that's an example of a design change that you can make that's going to make a significant difference to your finite element results. Okay. And so you don't have to do the diameter like that. You can just change the material. And so you can add another custom material in there to, that's going to work, and that's fine. Okay. Make sure it's a real material. So don't make up like Quasar 5959. That's like, a bajillion, a Young's modulus. So make sure it's a real one. So don't make something up. Okay. And then, problem 6, what I want you to do is I want you to rerun the simulation, but I want you to do it under 2 different loading scenarios. Okay. And so, we did a little bit of this in the last activity where I asked you to load the bike crank in compression, right, versus bending. And so this is kind of the next step of that, right? And so I want you to come up with two new loading scenarios that you can use on this signpost, something reasonable, right? And so right now what we have is a varying wind force and the weights of the post, right? And so, come up with, think about a freeway sign and what other forces that it would be under it would experience in practice, right? Maybe you have a bunch of, really fat seagulls that sit on top, right? And so that's a force that you can do. Or maybe someone's hanging, hanging something heavy like a washing machine or something from the signpost, right? And so those are some examples of, things that maybe not likely to happen, but could happen on the signpost. Okay, and so I want you to come up with two new loading scenarios and run the simulations, and then report on the results. Okay, and then problem 8 is just like similar to last activity. I'm giving you another geometry here that I want you to run a finite element simulation on. Okay, and so this one's going to be a lot less work just because it's I'm not asking you to do as much as I did up here. But this is just to give you more practice with, running simulations with assemblies. Okay, and so you can find the CAD file for this chair on the Canvas site. Okay, and there's a little bit extra here that I have to tell you about, and so that's kind of why the instructions are getting off. Okay, all right, and so this activity is going to be due next Friday, but I know there's a lot to this activity, and so if you guys need an extension, I'm fine pushing this back a little more too. But we'll keep it Friday for now. And then we'll see how you guys are doing on next week. Okay. All right. Any final questions before we wrap up for today? Okay. All right. So that's all we got planned. And so thank you guys for tuning in. Hope you guys enjoyed the activity. Have a great weekend, everyone. And I'll see you next week.
still, I don't understand why. it's not-
Yeah. Let me see the full definition. Yeah, can I check the, can you go back to work? Can I check the? And so your density is 0.0975, so it should be inches pounds per acre. You can never trust. Everything else was.
Wood thing, but,
I would actually close this out. So all your settings will be saved, it's just need to update.
just figured when I changed. Here specifically, right?
Yeah, unfortunately for ANSYS, it's a bit inconsistent. So when you change the units, it's like example, that everywhere. But for Workbench, you kind of feel kind of one. And that is big.
It is what it is. I think like overall this is a really good program. And so like it's really not that pretty intuitive. Like they make it really easy with all options. Really good.
Yep, just resolve it. So everything else is safe, so.
And then I save it as what is it?
Yeah, so you go to Workbench and then you can export and then export it.
It's not like I can really mess with it on the student version since I have so many notes, but I can just take the screenshots and answer questions and stuff like that. And then I guess on my
That's what it is. That's it.
yeah, that's pretty much.
Go to your pressure. Keep slide, right? Yeah. Yeah, that's the shoot. Yeah. Let's try this. Let's see if the gravity is an issue. So let's go ahead and suppress the standard of gravity. Just suppress it. All right. Sometimes you have to do like a process of to suppress something, check and see if it works. Because usually sometimes it's by doing this, it kind of makes it. What is this? Check that again. Let's
Yeah,
just,
the context says experience and it's rough change.
let's check the definition. Okay, so it's not. All right, let's check this. Let's check this. Let's go. Bonded, okay. The last one. Let's try suppressing one of the two. So let's try suppressing. Suppress both that one and the pressure.
So it's that. The,
I think that's the whole.
yeah, so is that what suppress the
Unfortunately not. It's, you can do, the way to get text dominance is you can make it smaller. And so if you make the element smaller, go back to the text dominant. But honestly, for this one, most of the stress is gonna be on the channel. And so it almost like a was just use of the first one. So you can just leave those as text. I would focus the meshing on. And in particular, most of the stress. Yeah, so you can just do that. Okay. Yeah, so it's a little bit hard to see. So most of the stress is concentrated. And so if you want to see this clearly, you can go. You can see it. But sometimes you can see all the stress down here, and you have nothing up here, which is expected. If you think of like you might have built, so the pillars of the building, those are going to be supporting. So same thing. So the post is going to be supporting. The sign itself is not really supporting. That's one. Yep.
Yeah, that wasn't the issue. Still bad. Yeah, and also, I mean, it's still right.
Yeah.
It's pressure, it's correct, right? Well, let's see.
Let's go. Let's check this out. The plus arrow. Yeah, no problem. See you guys. Sign.
Okay, that's right. It's gotta be the contact surfaces, because look what it's telling me. Contact status, experience and abrupt change. And results possible contact. And then like if we look at the stresses, like it's all concentrated in this little area of this contact.
Oh, it is.
Right here. Yeah, because that's what I was showing you earlier. It's like it's all in that tiny little area. So it's gotta have something. It's probably separated. It's concentrating since it's so tiny.
Right.
It's concentrating all the stress.
Yeah, we can try forcing the mesh. Like we can try forcing the mesh on the post and see. Right now you have a pretty tiny element size. Usually you should, but I can see an issue where it might concentrate. Go to your mesh. Well, let's suppress the reflector. Let's just do it just based on the side. You check the body sizing, first body size. That's what it's supposed to. The body size. Let's change this to 3.
It's not size and shit.
Yeah, for the element size. Let me check because I know you changed the deep features. Let me check to see what mine is. That shouldn't make a difference, but
I think I can put it back to standard.
oh, is it? Let me check and see what mine is.
Oh, it's actually a lot smaller than that.
Yeah, it's.
Yeah. Is it true for both of them? Yeah, it's true for both of them. Okay. Yeah, try changing it to
That's gotta
whatever
be
this
it.
is.
Because I guess, oh, yeah, I didn't realize it was so small. Well,
What is it? 3.127.
yeah, 3.127 E minus E.
Why does it have the 2 zeros?
I think
It's just E minus 2.
yeah. Yes.
Same thing.
Let's just try to mesh it again. And then we'll,
Can I change it back to the standard 2.5?
Sure.
Because that should be old, so. Should I not suppress the refinement?
let's try it without the refinement first. And then we'll, if that works. Then
Do I need to update the mesh to?
if you hit solve, it'll automatically.
Oh, okay.
Solve will go kind of low.
That's why I had so few. Yeah, that's why I had so few elements before.
Let me close the zoom out.